Hi, I'm Iason Sarantopoulos and I will present you our work with Marios Kiatos, Zoe Dulgeri and Sotiris Malasiotis titled Total Singulation with Modular Reinforcement Learning. When dealing with clutter scenes like the one on the right, the robot is not able to grasp the red target object, so the robot needs to rearrange the obstacles around the target in order to create the necessary space for the fingers to perform the grasp. The robot should totally singulate the target, which means that the closest obstacle to the target should be further than a distance threshold. In contrast to the partial singulation, total singulation allows the robot to use existing grasping methods and strategies which require free space all around the target. Our proposed solution is based on a modular reinforcement approach that uses different pushing primitive policies and selects between them with a high-level policy. The existing literature focuses mostly on partial singulation while using discrete actions and do not incorporate prior knowledge effectively. In this paper we use continuous actions, something which increases the available options for the robot. We also combine different policies that can be produced independently. We can use reinforcement learning, supervised learning, or even design the policies and then combine them together. We also integrate effectively prior knowledge via the primitives and the state representations. And finally, the method that achieves singulation in different environments. So we can manage equally a table with open limits and a bin with constraining walls on its limits. And this is shown during the experiments at the end of the presentation. In this work we define two pushing primitives, the push target and the push obstacle primitive, and they define the exact way that a push will be executed. We define each push as a line segment with initial position P1 and a final position P2. Firstly, we have the push target primitive. Take for example this scene with the red object being our target object. PO is the position of the target object, and the direction of the push is defined by an angle theta with the x-axis of the inertia frame. The initial position P1 is placed in the opposite directions, a direction in a distance di from the target, and the final position P2 is placed in distance dp, which is the pushing distance. The initial position P1 is always selected as the initial position that is not occupied by an obstacle. This means that it's not necessary to place the finger exactly beside the target object. To find the collision-free P1, we use the visual data, as we will see in the next slide. For this primitive, we learn the angle theta and the pushing distance dp, and we design di as described for avoiding obstacles. The second primitive is the push obstacle primitive. Here we place the finger right above the target object, and we push in the direction theta for a distance dp. And with this primitive we can move obstacles away from the target without moving the target, as you will see in this animation. And here we learn the angle theta, and we have a fixed pushing distance. All the parameters that we learn are continuous. We do not discretize the actions in this work. For the state representation, we use both a full state representation and a visual state representation. The full state representation is taken from the simulation and contains the bounding box of each object as well as their exact poses. The visual state representation is taken by rendering the 3D scene with a camera and acquiring RGB and depth information. From the RGB we extract the mask of the target, and from the depth we extract the height map of the scene. The mask is produced by a color detector or a more advanced object detection algorithm, and the height map is generated using the depth information. Both images are translated with respect to the centroid of the target to produce translation invariant features. We further crop the mask and height map to keep only relevant information for the predefined workspace. To generate the visual representation, we fuse the mask and the height map by assigning the value 1 to each pixel that belongs to an obstacle, the value 0.5 to each pixel that belongs to the target, and the value 0 in any other case. And this is the visual representation for the push target. Remember from the previous slide that the initial position for the push target is properly selected to avoid obstacles. This is performed with this state representation. Given the direction of the push, we move a batch of pixels in the opposite directions until we find an obstacle-free space. For the push obstacle, we take the same representation and we discard pixels that belong to obstacles shorter than the target and with a distance larger than the pushing distance. This reduces visual noise in the training as it removes the obstacles that cannot be affected by the primitive. The fused visual state representations are then fed to an autoencoder for dimensionality reduction, and the resulted latent vectors are the inputs to the high-level policy. Note that in push-target latent vector, we append the distances of the target from the table limits in order to learn how to avoid throwing the target off of the table limits. Then the high-level policy selects between the primitive policies, and then we feed the corresponding latent vector to the selected primitive policy, which produces a push for the robot. So for the training of the policies, firstly we train the push target policy with reinforcement learning. Since we use continuous actions, we utilize the DPG algorithm for training. We actually exploit the fact that we train in simulation to use an asymmetric actor critic, which means that we use the full state representation as input to the critic and the visual state representation as input to the actor. The reward in case of simulation is +1, which is a successful terminal state. If target falls off the table, we penalize the agent with -1, which is a failed terminal state. And if the push action increases the average distance of the obstacles from the target, we assign -0.1, and we assigned -0.25 in any other case instead of 0, in order to motivate the agent to simulate the target with a minimum number of pushes. The push obstacle policy is trained with supervised learning, so we create a dataset utilizing the full state representation from the simulator. So the ground truth policy pushes at the center of mass of each obstacle, and as we regress on angles, we use for training loss the cosine of the absolute error. So the high-level policy, the goal of the high-level policy is to combine the trained primitive policies. For that reason, we use the split DQN algorithm, which splits the vanilla DQN DPQ network to two separate networks, one network for each primitive. Each network takes as input the corresponding latent vector for the corresponding primitive and outputs the Q value for this primitive. So the primitive with the highest Q value is then executed. So we train each primitive policy separately in simulation, and then we train the high-level policy in order to combine them. First, we compare in simulation our proposed method, TSO. Here we compare it with two baselines, SDQN, the split DQN, and GTI. So in the table you can see the success rate, the mean number of actions until simulation, and the standard deviation of the number of actions. As you can see, the policy derived by the proposed method outperforms these baselines in terms of success rate. We also perform a comparison between using the asymmetric actor critic and not using it. Here you can see the success rate by using and not using it. The results show that using the asymmetric actor critic results to increase success rate, which means that this choice truly contributed to the results. Then we evaluated the policy in a UR5 robot with realistic objects that can be found in an office. The success rate in the real robot was 82.5%, a small drop from simulation, which means that the policy is transferred robustly. So in this video you can see the simulation of a target object, which is the small yellow objects at the center of this cluster of objects. On the left you can see the RGB and depth information, the output of the autoencoder, the primitive that the robot selects each time, and also you can see the output, the push that the selected primitive produce each time until the singulation of the target. Finally, we made the environment harder by adding walls on the limits of the support surface. This means that there are states which both primitives are useless and cannot change the scene, as you will see in the video. For this reason, we added a new primitive sliding primitive. With this primitive we can move the target object away from the walls and create the necessary space for placing the fingers for a push target, as you can see on this video. So this sliding primitive effectively creates the necessary affordances in order to use the other two primitives. So the modularity of the approach allows this addition of the primitive without retraining the other two primitives. Again, we only train the high-level policy. And in the table you can see the success rate in this environment when we use the primitive here, and we don't use the primitive, and you can see that using this sliding primitive makes a lot of difference. Thank you. Video, source code, and some more material will be available in this link.